In 10.1, we look at the study of conic sections. And the reason they're called conic sections is geometrically, if we look at them, if we take two cones and set them on top of each other vertically, like so. If you'd imagine slicing the cone parallel to this upper surface, then the region you would sketch out would be a circle. If you were to take and slice that cone at a diagonal, you would end up with something that was more elliptical, depending on how steep that slice was. If you sliced it through here, we would get a hyperbola. We can get parabolas. If we slice the cone on the edge, we can get parabolas. We can get lines. If we slice it right through the middle, we can even get a single point. So all of these are things that are considered conic sections. And we're going to look at parabolas, ellipses, hyperbolas. We've studied parabolas earlier in algebra, Math 112. We studied parabolas and said that the basic parabola, y equals x squared, goes through the origin, has a vertex at the origin, and looks something like that. And that's one way of looking at a parabola. Another form of an equation for a parabola goes like this. X minus h squared equals 4p y minus k, where hk is the vertex, p tells us the distance to the foci, and a line referred to as the directrix, and those are measured from the vertex. So, for example, if we have a vertex located here, we would have a focus at some distance p from the vertex, and we would have a directrix that same distance below it, and that directrix is actually a horizontal line. If you were to draw a line through the focus and the vertex, this is actually perpendicular to that line. The geometric description of a parabola is a set of all points that are equidistant from the focus and the directrix. If we pick another point somewhere that is on the parabola, it has to have the distance from the directrix to that point has to be the same distance from the focus to that point. We go up, let's say 5 units, we have to also be 5 units from the focus. So we do that on both sides, we get our parabola. And you can think of the focus kind of, if you think of a parabola as a mirror and you have light rays coming in, the focus would be the point at which those rays would reflect through. So let's look at an example. Let's suppose we have an equation. Let's see if we can get the book to pull up. No, we may have to just make one up. All right, let's look at this. Let's look at this one. Y squared minus 4y minus 4x equals 0. Now we saw a while ago we have x minus h squared equals 4p y minus k. we have basically y equals x squared, so we have a vertical parabola. And I didn't mention, if p is positive, then our focus is p units above the vertex. So if our vertex is hk, then the focus is p units above k, so h k plus p. The directrix, that's a horizontal line, so y equals whatever this y value is. This is p units below this y value, so k minus p. Now that's for a parabola that's going this way or this way. If p were negative, then the focus would be on this side, the directrix would be on this side, and our parabola would be like this. Now if we have a parabola going this way or this way, the y part is what's being squared. It's still y minus k, because k corresponds to the y value of the vertex, but then it's 4p x minus h. And that's what we have here. So what we want to do is we want our y part squared on one side, our x stuff on the other. So let's get the x part to the right side. We can add 4x to both sides. And we want to write this as a linear factor being squared. So we need to complete the square. So if we take half of this coefficient and square it, we get 4. So 4 is what we need to add to both sides. The left side factors, y minus 2 times y minus 2, or y minus 2 squared. We want to factor out the coefficient of x. So if we factor out 4, we're left with x plus 1. So this is our k value. If we consider this x minus negative 1, then this gives us our h, and this is 4 times p. So our vertex is at h, basically whatever makes this 0, k, whatever makes this 0, 4p equals, this whole coefficient is 4p, so 4p is 4, which tells us p is 1. So since it's a y squared, we know it's going to be this one or this one. So let's graph that. We pull up a grid. Our vertex is at negative 1, 2. So let's plot negative 1, 2. Our p was 1, and it's positive, so that means it's going to be to the right of the vertex. So there's our focus. Our directrix is p units to the left, so there's our directrix. So we have our directrix there. We can get other points if we want to. Let's just think about, if we were here, if I go 2 units that way, I need to be 2 units that way from the focus. So we would have another point there. If I'm 2 units from the directrix, I need to be 2 units from the focus. So I would have a point there. So we could sketch through our vertex through there, and that would give us a rough sketch of our parabola. Now another characteristic of a parabola is how wide or how narrow the parabola is, and that is what's referred to as the eccentricity. And the way we calculate the eccentricity of a parabola is c divided by a, where c squared is, sorry, hold on. I was about to get ahead of myself. I was thinking of eccentricity, but I was thinking of ellipses instead of parabolas. So we took an equation, we found the focus, the vertex, and the directrix from that equation. And we didn't write the equation, the directrix, but a vertical line is x equal, and the directrix has an x value of -2. Let's say we have another one. Let's suppose that we know we have a vertex here and the focus here. So that means our p-value is 3. We'll label these vertex and focus. So if we're 3 units above the vertex, then we're going to be 3 units below it for the directrix. So our directrix will be here. Let's see. So we know that P is 3. We know that our vertex is at 4, 1. So that's H and K. So if our parabola is one that's going like this, then that's of the form x minus h squared equals 4 times p times y minus k. 4 squared equals 12 times y minus 1. Read the equation of our parabola. If you're given the directrix instead of the focus, if you're given the equation of that, then you could figure out how far that distance is. We could find the focus from that. If you know where the vertex is and know P, then you can get the equation of your parabola. So that's parabolas. The next thing we look at is ellipses. And with ellipses, we still have an x minus h, a y minus k. There's x minus h squared and y minus k, both squared, added together. And if the larger value is underneath the x, then we call that a. If the larger value is underneath the y, then we would consider that to be a. So depending on what the value underneath the x term and the y term is, that determines actually which one of these is a or b. So we'll look in a second on what those refer to, but notice we have a 1 on the other side. So let's look at an example, and let's look at plotting an ellipse. So let's just make one up. Let's suppose we have x minus 2 squared over 4 plus y plus 1 squared over 16 equals 1. So whatever x minus whatever this number is, that tells us h. Y minus the -1, so k is -1. So 2, -1. Now, that's not the quote-unquote vertex of the ellipse, that's the center of it. If you think about the middle, the center, the centroid, center of mass of an ellipse, that's where that would occur. Now, since the larger value is under y, technically we consider this a squared. So a would be 4. So this would be b squared. So b is 2. So we have an ellipse centered at 2, -1. 2, -1. A is in the y direction, and that's 4. B is in the X direction, and that's 2. Now, we don't necessarily give these subscripts of Y and X. I just did that to let me remember that this is in the Y direction, but this is not a standard notation. This is a wages notation. So if this is the center of our ellipse, then this number tells us how far up and down we go from the center. So we go up 4 and down 4. This number tells us how far left and right we go from the center. So our ellipse, in fact, let's just let Smart sketch it. Our ellipse looks like that. Now, like a parabola, an ellipse has a focus. In fact, it has 2 focus, or foci. And the way we determine the focus is find out c. And for an ellipse, c squared is a squared minus b squared. So c squared is 16 minus 4, or c is the square root of 12, which as a decimal, what's that roughly? About 3.5, 3.46. So that tells us how far along what we call the major axis the foci lie. So if we go from this point to that point, the longer distance, that's considered the major axis. Remember, from here to here, that distance was A. From here to here, that distance was A. So the major axis is twice A. This other axis is known as the minor axis, and it's twice B, because we have B this way and B that way. Now the foci lie on the major axis, and they're C units from the center. So we go up square roots of 12 and down square roots of 12. So almost 3.5 units here, almost 3.5 units here. And those are the foci. Now, the interesting thing about the foci, or one interesting thing, is if we measure from the focus to a point on the ellipse to another point, if we were to add those 2 distances up, that's the sum, that total distance is a constant for a given ellipse. It doesn't change. So if I call this D1, D2, D1 plus D2 is a constant value. So that's a geometric way of thinking about what an ellipse is. It's a set of all points such that that distance is constant. Now, another way of thinking about an ellipse is how close to being round or how elongated it is. And we refer to that measure as the eccentricity. And the way we calculate it is C divided by A. Notice for an ellipse, C is from the center to the focus. A is from the center to the edge along the major axis. So A is always going to be larger than C. So E is going to be a value less than 1, but bigger than 0. Now, the closer C gets to the edge out here, then the closer C gets to A, which makes that closer and closer to 1, and that stretches your ellipse out. I don't know how well this is going to let us stretch the ellipse, but that makes it longer and longer. The closer or the smaller C gets, the more round our ellipse gets. So a circle is actually an ellipse that has an eccentricity of 0. If the focus is at the center, so C equals 0, so this distance is getting smaller and smaller and smaller and smaller until it's 0. 0 over anything is 0. So if our eccentricity is 0, that's a circle. So one way of differentiating conic sections is what their eccentricity is. The next conic section we look at is the hyperbola, and it has a different value for its eccentricity. So if C over A is between 0 and 1, we have an ellipse. Let's look at another ellipse. So let's see, let's look at this one. So let's begin by grouping our x terms together, 9x squared plus 36x, and our y terms together, 4y squared minus 24y, and move the 36 to the other side. So subtract 36 from both sides. Now also, keep in mind we want x minus h squared, y minus k squared. About to run out of room over there. So we're going to have some things on bottom and eventually a 1 over here. So we want to complete the square on these, but we also don't want a coefficient other than an understood 1 in front of the x. So let's factor out our coefficient. So if we factor a 9 out, we have x squared plus 4x. Here, if we factor a 4 out, y squared minus 6y. Now, if we complete the square, we take half of this and square it, half of this and square it. How much we're actually adding to the left side. Remember, this gets multiplied by what's out front, so that's adding 36, so we need to add 36 on the right side as well. If we put a plus 9 here, that's actually adding 36 to the left side again, so we need to add 36 to the right. So we have our coefficient. This factors to x plus 2, or x plus 2 squared. Here, this factors to y minus 3 squared. Those cancel and leave us 36. Now we have to have a 1 on this side, so to make that a 1, divide both sides by 36. And if we divide the right side by 36 and we have 2 terms, keep in mind we can actually divide each individual term by 36. So dividing the whole thing or each term by 36 is equivalent. So the 9 and the 36 reduce. The 4 and the 36 reduce. So x plus 2 squared over 4. Y minus 3 squared over 9 equals 1. So this is the larger denominator, so that's a squared. So a is 3. B squared, so b is 2. And our center is at hk, so negative 2 would make that 0. Or you could say x minus negative 2, y minus 3. So that's our center. Also, if we need to know c, c squared is a squared minus b squared. So c is the square root of 5. So if we want to plot that, let's come over, pull up a grid. So Our center is at -2, 3. There. A is in the y direction, 3 units. B is in the x direction, 2 units. So 3 units in the y direction, 2 units in the x direction. So we can construct our ellipse. There's our ellipse. We wanted to draw in our major axes and our minor axis. Our major axis has a length of 6. Our minor axis has a length of 4. If we want to put in our foci, remember C was the square root of 5, which the square root of 5, a little over 2.2. So we go a little over 2 up, a little over 2 down. That'll be our foci. If we wanted the eccentricity is C over A, which that's approximately square root of 5 divided by 3, about 0.75. So a larger value would make this would be a longer ellipse. A smaller one would be closer to being circular. So there are ellipses. Now the next conic section is hyperbola. Remember, those are the things that look like that or like that. So if we want to look at the equations that give us hyperbolas, we have two versions: x minus h squared over a squared minus y minus k squared over b squared equals 1. So that's for hyperbola that's going left and right. Notice the x part, the x squared comes first. If the y part is positive, if the y term comes first, minus the x term, then that's vertical. So if we want to draw hyperbolas, let's look at an example. Let's suppose we have x minus 3 squared over 9 minus y minus 2 squared over 16 equals 1. So how about, let's copy that over to a graph. So the center of that hyperbola is to the right 3, up 2. So the opposite of this, the opposite of that, 3, 2 is the center. And what we're going to do to get our asymptotes is we're going to sketch a box. And these numbers will help us determine that box. So if this is our a squared, a is 3. So we're going to go 3 units to the right, 3 units to the left, because that's in the x direction. This is b squared, so b is 4. That's in the y direction, so from the center we go up 4 and down 4. Now, if we draw a rectangle through those points, let's see. Get that rectangle. Now, if we draw lines across diagonals going through the center, those actually serve as asymptotes for this hyperbola. Now the question is, well, there are asymptotes. What points do we have? Well, since our x squared comes first, so remember we're going to be going this way. So this is 1 point on our graph. This is another point on our graph. C squared is a squared plus b squared for a hyperbola. Remember, for an ellipse, it was a squared minus b squared. So in this case, c squared is 9 plus 16, or c is the square root of 25, which is 5. C is the distance from the center to the focus of the foci, just like C was the distance from the center to the foci on an ellipse. So if you go from the center to the right 5 units, we get one focus. From the center to the left 5 units, we get the other focus. So our hyperbola is going to look like this. If we want the eccentricity is still C over A. Notice C is always going to be bigger than A, because if you take A, or to get C, you have to take A and then add stuff to it. So C is always going to be bigger. So since C is bigger than A, that is always going to be bigger than 1 for a hyperbola. So eccentricity between 0 and 1, an ellipse. Eccentricity bigger than 1, a hyperbola. Eccentricity of 0 is a circle. So let's see. Just real quickly, what do the foci have to do with it here? If you pick a point and measure from the focus to that point, and then that point to the other focus, just like for the, excuse me, just like for the ellipse, that's a set distance. Wherever we move that. And is that true? Okay, that was not. The difference between those is a set distance. Adding those together can't be a set distance because these go off to infinity. But it turns out we take d1 minus d2, which if our point is on this side, d1 is bigger. But if our point is on this side, d2 is bigger. So to make sure that's positive, take the absolute value. So the absolute value of the difference between d1 and d2 is a constant for a hyperbola. We can actually maybe figure out what that distance is. So from here to here, remember the distance from here to here, that's what was under the x, that's a, so here to here is a, here to here is a, so that's 2a. From here to here, that was what? What was I saying again? I was looking for this distance. So let's do this. Instead of calling that 2a, from here to here, that's c. From here to here, that's a. So C plus A is that distance. So we can call that D1. From the other focus to there, we want that distance. We take that total distance C minus that distance A, so that's D2. So from here to here, D1, from here to here, D2. So if we take the difference between those, C plus A minus C minus A, C minus C, notice those cancel. Minus the negative will make that a plus A plus A is 2A. So the difference between D1 and D2 will always be 2A for any hyperbola. Now the closer C gets to A, the flatter our hyperbolas get. So the closer E gets to 1, but is bigger than 1, we have really, really wide, flat hyperbolas. If the focus gets way out here, so that means our focus is out here, think about if our center is here, then that's A. C is a lot bigger, so if C gets farther from A, that makes narrower hyperbolas. So that's the characteristics of a hyperbola. So depending on how it's given to you, if you're given an equation or if you're given the location of the foci, the location of these vertices, then you can find A, you can find C. If you know A and C, remember C squared is A squared plus B squared on a hyperbola. So you can use that to find B once you know A and B. If we know our hyperbola is going sideways, we know the X term is first, and A squared is underneath it. The Y term is next, and the B squared is underneath it. If our hyperbola is vertical, then those are vice versa. A is always under the first term, B under the second for a hyperbola. So that's our characteristics of a hyperbola.